Hello class, today we're going to cover section 4.5, which covers simple harmonic motion, damped motion, and combining waves. So the first thing that we're going to talk about is simple harmonic motion. And what simple harmonic motion is just think of like a slinky. When you let them go hanging vertically, what it does is it goes back and forth, up and down, up and down. That is simple harmonic motion. It's just motion that is repeated. Typically what they'll do is they will have it done in a way where it's dropping. And so the formula, one of the formulas that you'll want to know is this one right here, where the displacement is the D, and the acceleration is your A. There's a theorem that goes with that, and that theorem also has an important formula to it. That's the formula there. There's two of them. There's one for cosine, there's one for sine. The amplitude is going to be A, and the period is going to be 2 pi over omega. And then from there, we'll be able to use that formula to solve for our problem. Frequency is simply the reciprocal of the period. And so if you know what the period formula is, frequency is just it being reciprocated. Let's go ahead and try to use this information to solve for one of our examples. And so in this first example, it says that suppose an object attached to a coil spring is pulled down a distance of 5 inches. So that's important. The direction is important. It's going down and it's going 5 inches. From its rest position and then released, that's going to cause the simple harmonic motion, and it oscillates for one oscillation is 3 seconds long. That's information that's important. Also, develop a model. Basically, they're asking us to come up with an equation that relates to the displacement of the object from its rest position after t seconds. So that down distance is our amplitude. So it's going to be down a -5, or we can think of the amplitude as the absolute value of that. But when we use the formula, notice that in this formula, we don't have the absolute value piece. We just have the amplitude A. And so our A here is that down -5. The one oscillation is the period. So that's important to know too, that the period is going to be the time it takes to do one oscillation. And so in these problems, you're going to have to see period is time it takes for one oscillation. And so we know that 2 pi over the omega is 3. And so we can solve that and see that our omega is going to be 2 pi over 3. And so the formula that we're going to use in this case is going to be the cosine formula, just because it's the first one written. And so we're going to get D is equal to a -5 cosine of 2 pi over 3 t. This is the equation for this first example. So actually pretty cool. That is our answer to this first problem. Again, these formulas are good and critical for you to know and use. Let me go ahead and do another example for you. All right. So in this example, it says, suppose that the displacement in d meters of an object at a time t satisfies this equation. So we're looking at this equation here. And remember, the formula was A sine of omega t, right? And so it says, describe the motion of the object. And so we see it says, suppose that the displacement of an object at time t satisfies this equation. by the theorem that we had, we know that this is going to be a simple harmonic motion, meaning it's going to oscillate back and forth. And so we know that that is going to be a simple harmonic motion from the formula we have. And it says, what is the maximum displacement from its resting position? Well, remember, the A is what dictates what the amplitude is, and that's where we have our maximum displacement. So the A in this case is 10, so A is 10, and that would be the maximum displacement. And since we don't know what the units are, we'll just say it's 10 units. Oh, we do know the units. They are meters, and so it is 10 meters. Okay. Then it says, what is the time required for one oscillation? And so this is important that we know. We need to remember that for C, that 2 pi over omega is the period, and the period is what measures one oscillation. So what information do we have? We have 2 pi over our omega, which is 5, and so this is how many seconds it will take for part C. So this is the answer to part C. All right, for D then, we need to remember that the frequency is the reciprocal of the period. So frequency is going to be omega over 2 pi, simply the reciprocal, and so that's going to be 5 over 2 pi. And that's the number of oscillations that occur per second. And there's that example. Okay, now let's talk about damping motion. And so there's an important formula that we're going to need, and this is that formula. And again, the amplitude is going to be A, and the period again is going to be that 2 pi omega. So understanding this formula is not too bad. And then we need to understand also that M is mass. So in these problems, we're going to be given some information about weight, and we're going to be able to go from there. So let's see if we can solve a problem doing this. Here we go. So in this problem here, they're giving us the damping equation for this problem, and they're asking us to analyze it. And so what we can see is that the displacement of this equation is a product of two functions. So we have two functions that are being used here. We have this function and we have this function here. Now both of these functions we're going to be using, and so what we need to remember is we can use the absolute value property for this. And so in the absolute value property, we're going to get that the displacement of t in absolute value is going to be equal to e to the negative t over pi cosine of t in absolute value. And then we're going to be able to break that up into two functions that are multiplied. And then what we need to realize is that the biggest value that cosine of t can be, so cosine of t, the absolute value of it, the biggest value it's going to be is 1. It's going to fall between 1 and negative 1. And so since that's the biggest value it's going to be, we're going to use that maximum value and just say it's 1. And so that means that e of negative t over pi in absolute value is going to be bigger than or equal to this function right here because of this condition here. Because if cosine is anything smaller than 1, you agree that this is bigger. And so what we can say is this is e of negative t over pi. So, but we should put the plus minus there. And so what we can say is therefore, negative e of t over pi is going to be less than or equal to the damping, which will be less than or equal to the positive e of negative t over pi. So if we graph this, what this means is, this means our d of t will fall between these two curves. And so the two curves are this guy and this guy. And so we can see in the picture that I drew here from a calculator, that I got from a calculator, our actual function is this guy right here. And we can see my drawing kind of terrible, but trying to follow it there, but you guys can see it, is between the two functions. The red function, which is the positive case. In fact, I'll do that so you guys can see. I'll make this red. That's the positive, and the black one below is the negative case, which I have over here in blue. And then we see that the function is actually falling in between those two curves. So it's bouncing back and forth between those two curves. I can see where this is a little bit tricky, but for both sine and cosine, this is going to be the trick. So you're going to have to remember that cosine and sine are both restricted to be less than or equal to 1, because it oscillates to its greatest value of 1 and its lowest value of negative 1. Okay, let's do another example, and this example is adding up two functions, and so we can think of this as two separate functions of x and sine of x. And so the way that I'm going to do this is I'm going to kind of make a table. I'm going to say sine of x, I'm going to say x sine of x, and then I'm going to go x plus sine of x so you guys can graph this. And so the values that I'm going to use are just the values that we have here. 0, pi over 2, pi, 3 pi over 2, and 2 pi. And so for x, it's just going to be all of those values, correct? So that is the value for x if I plug in. Now sine of x, sine of 0 is 0, sine of pi over 2 is 1, sine of pi we know is 0, sine of 3 pi over 2 is a negative 1, and sine of 2 pi is 0. So then what we're going to do is, to get this bottom one, what we need to do is just simply add them. So 0 plus 0 is 0. 1 plus pi over 2, when we use a calculator, is 2.57. 0 plus pi is going to give us 3.14. And then 3 pi over 2 minus 1 is going to give us 3.71. And then 2 pi plus 0 is 2 pi, and that's the same as 6.28. So when we go to graph this, at 0, it's going to be 0. At pi over 2, it'll be 2.57. It'll be something about there. At pi, it's going to be 3.14, which will be something about there. At 3 pi over 2, it'll be 3.71, which is a little bit higher value. And then at 2 pi, it's going to be 6.28, which is somewhere about here. And so this curve is going to look like something like this. And that is the graph of x plus sine of x. So when we're trying to add or graph two functions, we're going to find each one's function and then add their y values to be able to then plot the points. I hope this has been beneficial. If you have any questions, please feel free to ask. As always, all the best.